are, you know, each function is kind of like a machine. So if two functions are inverses, it would be like, I don't know, throwing some chocolate, peanut butter, salt into a machine and it pops out a peanut butter cup. That's machine 1. And machine 2, if it's its inverse function, you'd put the peanut butter cup into that new machine and it would break it all back down to your separate peanut butter, chocolate, salt. Do you like that? I thought that was a good analogy. Anything that brings a Reese's to my mind is a good thing. So, you guys are used to writing inverses. I do know that. And obviously, if two functions are inverses, you plug a 7 into the first one, and maybe it pops out a 9. You then take that 9 and plug it into the second one, and it will pop back out that original 7. So if you do f of g of 7 and you get 7, there's a good chance they're inverses. Not always. It has to work for every single number. And one could happen by coincidence, but usually multiple ones don't happen by coincidence. So that's really the inverses you know about so far. There's this generic approach of that we will do more with, and I'll make you use this method to prove whether or not they're inverses. And that is test f of g of x, make sure you get x, but also the reverse has to work. It has to work in both orders. So g of f of x has to equal x as well. So on the first example, if we were using this definition to prove it, we would first have to do f of g of x, which would be taking this g of x function and plugging it into the f. So that would be 3 times, and we're going to replace the x here with x minus 2 over 3 plus 2. And then you simplify that. So the 3 times the fraction is just going to cancel out the denominator. You have x minus 2 plus 2, which is just x. So that direction of it works. We also then would have to verify with g of f of x, which is going the other way, taking your f of x function and plugging it into your g. So right away, I'm replacing this x with a 3x plus 2 minus the 2 all over 3. And obviously in your numerator, the 2 minus 2 would reduce, and then you just have 3x over 3, which is just x. So, yes. In order to answer yes, they both have to work. In order to answer no, you only have to show that one of them doesn't work. And it may be with a no answer that you test the first one right off the bat and it doesn't work, so you can stop. Or it may be that you test the first one and it works, but you go the other direction and that one doesn't work, and so then you would still answer no. Okay, so that's if you're given 2 and you're asked to verify. On another note, writing the inverse, which you definitely did a lot of last year. Yes? So, does anyone remember that process? Go ahead, Abby.
Didn't you switch the x and y?
Perfect. Because, by the way, that is the go-to on inverses. If you're looking at 2 pictures of 2 different functions, they're going to be inverses if every single point on one is flip-flopped to give you the points on the other. For example, if 1, 3 is on the original function, that would map to 3, 1 on the other function. If 2, 5 was on the first, then 5, 2 would be on the second. Everything is about x's and y's flipping. With that, same thing with domain and range. The domain of the initial function is going to actually be the range of the inverse. And the range of the original is going to be the domain of the inverse. All things x and y's flip-flop. And with that, when you look at 2 functions that are inverses of each other on a graph, what's the transformation appearance that you'll see? What's the connection between 2 graphs of inverses if you look at them visually? For example, I'll show you these 2. Raise your hand when you remember. Here's the first one, 3x plus 2. And the second one is x minus 2 over 3. How is one a transformation of the other? Perfect, yep. They'll always be flipped over the line y equals x, and that's because if you're reflecting a point over y equals x, the rule is flip the coordinates. So like 0, 2 becomes 2, 0. Oh, that's another thing I haven't mentioned yet. The y-intercept of the original becomes the x-intercept of the other, and the x-intercept of the original becomes the y-intercept of the other. All things x's and y's flip-flop. Then you solve for y just to get it in function form, so you'd subtract 1 here. And then how do I get y all by itself? Andrew? Sorry. Yes. Cubed root of x minus 1. So this would give us y equals the cubed root of x minus 1, but we don't really use y's in adult math. Instead of f of x, we use f inverse of x equals the cubed root of x minus 1, and there's your inverse. And I'll show you these so that you, again, get another visual. There's your cubed root function. Or I'm sorry, that first one was your cubed function, and the second one is your cubed root function. Do we see the symmetry? Okay. Do you see how it looks a little off? Does anyone know why that is? By the way, I'm on a window of negative 10 to 10 and a negative 10 to 10 window. Anybody know why it looks slightly off and not, doesn't really look perfectly symmetrical? If I actually graph the line y equals x, which we know y equals x is a perfect kind of diagonal line at a 45-degree angle, right? That kind of maybe makes it look a little bit better. I don't even know if you agree with me. Do you think it looks a little off? Or no? You don't? Well, it does. It does. The reason it does is because we're looking at a square. Negative 10 to 10 and negative 10 to 10 should be a square, but your screen's actually a rectangle. Yes? So even if I alone look at the line y equals x, which we said is supposed to be at a 45-degree angle, if you actually looked at that, that wouldn't be at a 45-degree angle. It would actually be kind of slightly smaller than that just because the screen is stretched into a rectangle. Anyway, that's a side note. Find the inverse of x squared. So again, if we flip-flop, square root both sides, what do we have to remember? Trissa? Yep, plus or minus. Anytime you take the square root of both sides. Cubed root, you don't remember that, because that's not how cubed roots actually work. But square roots or fourth roots, you have to have a plus or minus out in front. So this one's a little bit interesting. If we go back to this original function, which looked something like this, we can say that this is a one-to-one function. We did that last year, one-to-one functions. I'd be impressed if you remembered what it was, though. There's functions, and then there's special functions called one-to-one functions. Anybody? Morgan, did you maybe have a halfway hand up? No? What makes this a function? Yeah, go ahead, John. Passes the vertical line test. What makes this a one-to-one function, because it is that it also passes the horizontal line test. which means when I flip it and I draw a picture of the inverse function, if this one passed the horizontal, then your inverse is going to pass the vertical. There's those x's and y's all flipping again. And if your original is a function and your inverse is a function, that's what makes something a specialized function called a one-to-one function. Okay, one-to-one functions pass both the vertical and the horizontal line test. The horizontal line test on the original is really just to ensure that the inverse will pass the vertical, that the inverse will also be a function. That's not going to be the case here, because we all know what the x squared graph looks like. And yes, it is a function, but it is not a one-to-one function because it fails the horizontal. And the reason it fails the horizontal is because its inverse will not be a function, will not pass the vertical. Because here's what positive square root of x looks like, and here's what the negative square root of x looks like when you flip it over. And although this to this is a reflection across the line y equals x, yes, they are inverses, but this is a function and this one is not. Therefore, collectively, this is not a one-to-one function situation. Are there any questions on that? Does that sound familiar? That conversation? Raise your hand if that sounds like you did it last year. Oh, no. You think so? You know, it doesn't come up a lot, so we don't really overly test it a lot in class because it doesn't come up on the Regents a ton. But anyway. So there it is, the horizontal line test. If a function passes this test, then its inverse will also be a function. And therefore, it's called a 1-to-1 function. If it passes both. Any questions? Okey-doke. Here we just have to sketch the graph of an inverse. So again, we're going to take just the critical points and flip-flop them. So -3, -2 will become what, Bailey? Sorry, you're still writing.
What you added in the numbers?
If I want to invert the point -3, -2, what will it become?
-2.
Perfect. Sorry, you can go back. -1, 0, which is an x-intercept of -1, will become a y-intercept of -1, 0, -1. And then you can sort of connect those. And then 6, 2 will become 2, 6. And that's our image, and you definitely can see the line of symmetry, y equals x. So what one today, ladies and gentlemen? Days like this, we really don't mind being in school, right? Because what else would you be doing? You know? No? True. Sleeping. Maybe you would be. I would not be with 2 children running around my head at home. I would not be sleeping. In fact, my 1-year-old likes to smash me in the head with a remote control if I try to snooze on the couch. It's not intentional. He's a little young yet, and he's like a baby, but still. And watching TV, it doesn't work because I just get bothered to watch Blaze and the Monster Machine. Are we fans?
My brother watches that.
How old's your brother?
He's 4.
Cute. Yeah, my son's 3.5. All right. Lastly, this one's a little bit special because it says to find the inverse of f of x equals x squared minus 1 if x is greater than or equal to 0. Now, there's a reason why it limits the domain. So here's the graph of x squared, the parent graph of a parabola, minus 1. That's the whole function. Why do you suppose it only wants us to look at where the graph has an x-coordinate greater than or equal to 0, do you think? In light of our conversation on the front side. Go ahead, Mitch. Right. Because right now it's failing the horizontal line test, but if we only look at it along that given domain, now we can say that this inverse will also be a function. Yes? Just to talk about it before we get started on this. They're limiting the domain, which as a result is sort of going to limit our range as well. What will our range be of this? Y has to be what? Greater than or equal to -1. Perfect. And then we're going to go ahead and write the inverse. So x equals y squared minus 1. Add 1 to both sides. Square root both sides. So y has to equal plus or minus root x plus 1. But here's the thing about this. This is where that deeper level of thought's going to come in. On our original, x had to be greater than or equal to 0. So what does that mean for our inverse function? If on the original x has to be greater than or equal to 0, what does that mean on our inverse? What? Y has to be greater than or equal to 0, because all things x's and y's flip-flop. Which means where we are right now is that y has to equal plus or minus, which actually is not true. It would have been true if we hadn't limited the domain and we were just doing the inverse of this. But because we had a limited domain, now we have a limited range. And so if y has to be greater than or equal to 0, we can get rid of that plus or minus and just keep it plus. Follow that? And this you're going to see why this is the case for two reasons. In the original, y had to be greater than or equal to -1, which means in our inverse function, x has to be greater than or equal to -1. But we would have known that anyway, or should have known that anyway, because when you're taking square roots, you have to take the square root of a non-negative, because it can be 0 too. Non-negative is how we would say that. But yes, so if we set up this to look at the domain of the new function, knowing that x plus 1 has to be greater than or equal to 0, that would produce that anyway. Okay? But this part we definitely have to think about. Because the original function was limited, somehow our inverse function is going to be limited. And then I'm just going to change this to f inverse of x equals the square root of x plus 1. And those are my domains and ranges. So if I think about what just the square root of x plus 1 is, that's the parent graph of radical x shifted how? Parent graph of radical x shifted how?
Horizontal shift to the left.
Left 1 unit. So that's going to be, instead of being here, it's going to be left 1 unit, and it's going to look like that. And all sorts of things are seen here. The y-intercept of the original just became the x-intercept of the inverse. And you get that symmetry across the line y equals x. Okie doke? Any questions on inverses? Yeah.
Would it be true for all functions that the inverse is, I'm not sure if it's the opposite of what's being done with the x, and the opposite of anything that's being added on to x, I guess? I'm not sure exactly what to phrase it. So like, in the example, the inverse of x squared minus 1 is the square root of x plus 1. So, for example, anything that's x squared would be the square root of x.
Mm-hmm.
And then if it's plus or minus something, it would be the opposite of that. Is that always going to be true?
Yeah, because think about when you're switching the x and y coordinate and then you're solving for the other one. You're doing opposite operations to get everything over. One thing I would just caution you on is, like, for example, like this one has a -1 that's a vertical shift, but that +1 actually becomes horizontal. So it's not always, how would you wouldn't necessarily know whether it's root x plus 1 after the fact or root x plus 1 underneath the whole thing, which is why, and conceptually that is accurate, but you want to, especially as they get more complex and there's more layers, you want to go through just the process. It's not a hard one, but so often in Algebra 2, and hopefully you guys have grown out of this by now, like kids will try to write the inverse and do it all mentally. I would never do that. Because although there's like little things you can notice like that, it's just a recipe for disaster, because things that you really can't anticipate happening actually, don't happen the way you see it. And I can give you a great example because my Algebra 2 kids just took a quiz and this kind of stuff was on it. And I was like a little bit driven crazy on a problem like this. They were given the inverse and they had to find the original function, which is the same as being given the original function and having to find the inverse. The process is all the same. And the number of kids that didn't show any work was unbelievable. So, -3/4 x plus 2, they just negated everything. Well, that's not how you find an inverse, right? If you negate everything, you're actually flipping something vertically over the x-axis, right? If you take an f of x and you negate it, you're actually flipping it vertically. That's not what an inverse is doing. So I'm looking at all these, and I just was thumbing through prior, and I couldn't believe the number of people that didn't show work, because they're thinking, and I've told them 1,000 times, you can't do this without showing work. I mean, some kids can. I mean, I could, but I would still have to think through those steps, and why make yourself do all that mental work and risk a mistake and like miss seeing something visually? Just write it down. So the people who just don't show work, they all get it wrong. Then you've got someone who actually did the process and they get it right. But no work, wrong. They did all the work, they got it right. They did all the work, they got it right. They did all the work, but there was a whole, well, this person either cheated or got lucky. What did this person do? I don't know what this person did. They didn't actually just rewrite this and switch the x and y. No work, got it wrong. They did the work, got it right. They did some work, got it right. Those must have been the kids that had their test longer, because when I first looked at the first few people who handed in, it was pretty bad. What did this person do? Take a minute, look at that. We can play teacher. Who got my points already today? Joe? Which means we're at Bailey. Bailey, can you comment on what this person did wrong? No. Andrew?
They didn't divide by -3.
Right. When they were solving for y down here, to get rid of a coefficient, you divide by the coefficient or multiply by its reciprocal. They didn't multiply by its reciprocal, they multiplied by its opposite reciprocal, which I know those two words, opposite reciprocal, kind of go hand in hand for a lot of you guys because you did so much with perpendicular lines in Algebra 1 and geometry. But reciprocal just means flip it. So if it's negative, it stays negative. And so yeah, they didn't do that. But at any rate, this was I was a little bit frustrated by that problem. And you don't, Aiden, want to do it in your head, even though sometimes you could think through that and notice some patterns. Okay? All right, so your homework is there. We have 10 minutes, so I will post it up there. If you prefer to get a book from the back, go ahead.